All right, so problem number 9. Can you remind me of the problem?
12 people are lined in 2 rows of 6 4 4.
10 people, huh?
12.
Oh, 12.
12 people are lined up in 2 rows.
Okay.
Of
And then?
6 4 4. Here's
I didn't read the So 12 people are lined up in 2 rows of 6 for a photo. How many ways can they be arranged if the tallest person must stand in the back row and the 2 shortest in the so in the back, 1 tall in the back, 1 tall person in the front, 2 short persons. Very good. Yeah. So what are we gonna do? So generally, we can do this problem in a few different ways. So we can. Here is one of them. First, let's choose who is where. So so we will put that tall person on the back. So 1 tall person in the back for sure, already there, and 2 short persons in front, already there. So then, what do we need to decide for a remaining 9 people? We need to decide which 4 are we going to put in front. Do you agree? So what's that? We can do it in the 9 choose 4 ways. So hello, Jianbin asked me about this problem number 9 from the prep test. So like 12 people are lining up in 2 rows, and then tallest person should be in the back row, and 2 shortest persons should be in the front row. So we started to solve the problem. So we said the following: we'll put that tall person in the back because we have to. That's a constraint. And then those 2 short persons in front. And then where's our freedom to do configurations? Now there are 4 more spots here in front. And then among 9 persons, we decide which 4 persons will be there. I did combinations and not permutations because here I'm just deciding who's in, who's out. And now, what did I do here? I fixed exactly who's in front, who's in the back. And then what can I do? Now, among those people in the front, there are 6 of them. I can shuffle them however I want. So generally, number of configurations or number of lineups is 9 choose 4 times 6 factorial times another 6 factorial, because there's no restriction how I can shuffle within each row. That's it. There are probably other ways to immediately start with the permutations and not even involve combinations. So what would be the second idea? So first, it would be more complicated, I would say, but doesn't matter. We will choose, and I hope we get the same answer. We choose in the first row. Which so not only we said, oh, short persons are in the first row, nothing to decide. No, we want to decide immediately where to put them. So in how many ways can we do that? So there are what? There are 6 spots. We can do it. We can choose those 2 to host these 2 persons first. But then it's not only important which 2 they get, but who comes on the left position, who comes to the right position. So it would be 2. Basically, yes, if they're different persons, no, it's a better way to think of it this way. First of them in 6 different ways, and then the second one in 5 different ways on the remaining spots. And then what else? 6 times 5. So now what I have, I know exactly where these 2 persons are. So it's short one, whatever we labeled. And then, so for each of those 3 options, now what do? We need to place somewhere the tall person. In how many ways can we place the tall person? 6 different ways. 6 ways, wherever that tall person is. And now I can think of this, it doesn't matter anymore who's first, second. We'll just, hello. Can you see us here?
Yeah, can you hear me?
Yes.
All right, cool.
So we are doing problem number 9 from the prep test. So
Okay,
people lined up in 2 rows, and then there's
that's the photo one, yeah.
yes. So generally we already established one solution, and that is we choose 4 spots for those remaining persons, and then who will be in the first row, and then we do the shuffling. How would the second idea go? We said what, 6 times 5 to host short ones, and then 6 different ways to host the tall one, and then what now? Then there are 9 remaining, so 9 factorial. Because we don't care anymore. We just go 1, 2, 3, 4, 5, 6, 7, 8, 9. So it doesn't matter who comes where. What's our reasonable hope that this is what? That we get the same number. You know, if we don't get it, one of the configurations was not counted correctly. So what would it be? This is 9 factorial over what? 4 factorial times 5 factorial times 6 factorial times 6 factorial. What would that give us? I already have 9 factorial there, so that's good. So what's left in the lower solution is 656, and that's exactly true. Why? Because what's this? 9 factorial should be kept. This is 4 factorial, 5 factorial. This is 6 times 5 factorial. This is 6 times 5 times 4 factorial. We cancel 4 factorial, we cancel 5 factorial. 9 factorial, 665. 9 factorial, 665. So that means that probably both configurations are good. So you see, it's up to you. How do you kind of organize the counting as long as it's consistent with the text or with the configuration. And sometimes you remember that sometimes it really happens that actually our language is not precise enough. So there are probably a couple of different ways to read the text and interpret it. Although I will try on the final for sure to make it clearly readable.
6 times 5 the same as the 6 choose 2 that you had before?
No, I started 6 choose 2, but then I would need times 2. Why? Because not only 6 choose 2 is which 2 do you choose for these 2 guys, but then when you know which 2 are assigned to them, you can put them this way or this way, and that's times 2. So then I said, why would I think of it that way, which is correct. So generally you can think of it as 6 times 2 and then times 2. Then when I said, why then, if the order is important, why don't I just place them regularly? 6 ways to choose the first person and then 5 ways for the other, because they are recognizable, person 1, person 2. Zhang wants to come in, or he's waiting for someone. Oh, we'll see. We'll see. All right, he knows that we are here. Does this make sense?
Yeah.
So it is, not who knows how hard problem. Hi guys, come in. But it needs a little configuration. It's not a lot, just call the formula. So generally you need kind of to think about the ways to build this configuration. And sounds also like how do you write a program to satisfy some conditions. That's what this design really has. Once you have design, then you start calling for it. Something about this one, different problem or something similar? Yes.
Can I see the next one, number 10, where the ball is dropped from
Are there any questions about this one? Yes.
I was just going to explain in the first solution.
Here?
Yes, just how they can.
Because I said the following. What was that? So I would play tall person just for sure to be in the back. Tall person for sure in front. And when that's taken care of, what do? I can mess it up. I can do whatever I want among the people in the back. I can shuffle them on these 6 seats as long as I don't send someone to go ahead. So tall person will stay behind, and I can shuffle them however I want. So that's 6 factorial for shuffling in the back, and 6 factorial for shuffling in front. That's what it is. Because each configuration in front could be matched with an in the back. None of them ruins the problem or that double counting. This sounds to me like a simpler idea, cleaner to control. You know, when you place them, then you shuffle them. Here we need a little bit more, control of things. See, something else. All right, Stephen. What was? With the bouncing ball.
Yeah.
That's a question from your calculus 2 book. You know, when you did power series, that's what you did, maybe with infinite many steps or whatever it was, but the setup is there. Let's see how it works. Generally, the crucial thing there is to memorize one of the formulas for the sum of geometric sequence. So either summation formula for powers or for geometric sequence, whichever one you find useful. Let's say I will use the following formula: sum of r to the I goes from 0 to n, which is, by the way, what? 1 plus r squared plus r to the n equals 1 minus r. Yes, if it's less than 1, why not? 1 minus r to the n plus 1 over 5 minus r. Usually in calculus 2, you'll only deal with r's by absolute value less than 1. That's why this is more convenient. For finite ones, we also deal sometimes with r's greater than 1. That doesn't matter. So here's the formula. Be careful. So n is here. Last member is r to the n. You go to the r to the n plus 1. And what else? If you think of this as geometric series, then first member, but this one must have 1 as a first member. So this is your A1, and this is basically what? This is A2, this is A3, this is not AN, this is what? A n plus 1. So if you use that other configuration, I will cross it so that we don't have double idea. So I like summation formula. And then, can I have the text? Sorry. I should have brought it. So the only thing here is to be careful what's your last index, 6 or 7 or 8 or whatever it is. So it says the following. It is dropped from the height 20 feet. So that's, and then it says each time it drops h feet, it rebounds 0.72 h feet. And then they say, find the total distance traveled by the ball until the moment it hits the ground for the 7th time. 7th time. And that's probably the only thing. There are two things. Two things to kind of control. So what are these two things? This is the first hit. Okay. So before that, and then what happens after that first? You go up 20h. 20h. H is 0.72, we said. Or R. R equals R is 0.72. Yes. So you go 20 times R up. But then what also happens? You also go for the same distance down. So you go 20 R down. So this is up, this is down. What's that? This is before your second hit. So I'm basically building a recursive formula just for safety. So what can we say? If it's second hit, what happened before the third hit, not after, before third hit. Now it will rebound a little shorter, 20 R squared, and then again, no, it will go up, 20 R squared, and then down. So this is 20 R squared plus 20 R squared. Theoretic evidence. So then what? Before the seventh hit, by analogy, what can you say? What is that last up and down before the seventh hit? Exactly. 20 R to the 6 plus 20 R. So that was the only sensitive part. Is that R to the 7th or R to the 6th? Every time you multiply by R, and there is that doubling. And then what? There is one little problem, and that is you don't have doubling in the beginning because it didn't rebound, you started from height. So generally to restore the symmetry, I like to kind of artificially put another 20, but of course subtract. You don't have to, but I'd like my powers to start from 0. It's more convenient for the formula. Otherwise, this guy would go on the side, and then I would add the others factor r's. It's all possible. I think this is simple. So I'll say the following: S equals, I'm not going to call it S equals S6 or S7. It will be sum of what would that be? 2 times 20 times R to the I goes between 0 and 6. Everybody okay with this? So when I equals 0, this is the first part. When I equals 6, this is the 7th part. From 0 to 6, there are 7 steps. Of course, don't forget to do what? Subtract what?
Subtract the 20.
What's it?
20, yeah.
Can you see it here in the corner?
Yeah, I can.
Good. And that's it. So now what do? We factor out 40. We apply the formula. Formula is 1 minus R to the 7 over 1 minus R and minus 20. That would be 40 times R is 0.72, so this would be 0.28. This is 1 minus 0.7 and minus 20. And then you put it in calculator. Does anyone have a result? I will post the solution, but does anyone have it?
I think it was 108.53 or something like that.
108.5?
Yeah. Or 3, yeah.
Okay, 108.5.
Yeah.
That's it. Thank you. Makes sense, everybody. So generally, as I said, it's really like little recursion to see precisely what are the ingredients. So before the first hit, thank you, Steve. So you do the counting when it hits. First hit, I have just half of the story. Second hit, I have half of that story for no R's, and story with that double story with R's, and then keep going. By analogy, it will be 20R6, 20R6. We recorded that, called summation formula. Does this make sense, everybody? And then, of course, the only difference is in calculus 2, they ask you total. If it goes forever, then you would take a limit. This guy would go to 0, and you would get just 1 over 0.28. And that would be very close to this, because now it really starts traveling less and less. So what is this? This is basically that section 2, where we, section 5.2, where we covered some algorithmic sequences, and those are arithmetic and geometric. So, besides doing those fancy things in section 1 and section 3, I thought it's a good idea to make it sure that everybody can do these problems that are still doing pre-calculus. In pre-calculus courses, there's a similar topic, so we better be able to do that. I know everybody's face. I'm not sure that I saw you. Can you remind me your name? Oh, Minge. Yeah, okay. Yeah. Yang?
Yeah.
Oh, yeah. Okay. Yeah. I rarely ask my students for their name in the finals week, but in online course you can. All right, next question, if any.
Number 14.
What was that? Can you remind me?
It's like true or false. It has odd number of inside. But the number of vertex is completely
Okay, let me erase this. Okay. So that's actually, you can just read that that theorem in the notes, but I don't mind discussing it. I know it's a good idea. So it's precisely how did I formulate it? So theorem. What would that be? Full binary tree has what?
Has odd number of vertices.
Binary tree has odd number of vertices. So choosing this problem, I want to give you a hint for the final. What is the hint? Number one, there will be one proof about graphs, but not those long and complicated. There are a few proofs if you read the lecture notes in detail. Few of them are really tricky. Like you go around the tree and then you reverse the order, cut off, do some induction. There are a couple of them that really need very precise organization. I'm not going to ask any of those complicated ones, but those where you need to show me that you understand basic definitions and that that also you can present a logical argument like what we started in the course in the beginning. So now you see, instead of asking about integers, I want you to show me that about graphs. For example, that a graph has Euler path if and only if what? All the degrees are even, or there are what? Exactly two odd degree vertices. That's a fairly simple proof. So generally that might be reasonable. I'm not saying it will show up, but that's also reasonable mechanics. Yes.
In this question, you also said if the number of vertices is 2k plus 1, then k vertices are internal and k plus 1 are external.
Yes, that's exactly, yes.
So is that something that you want us to prove also?
Yes, yes, because that's the whole statement, yeah. So how do we prove that? Generally, first, what do we know about trees? Tree, that means the graph, simple graph that's connected. And what else? No? Cycles. All right. So, what happens? And then what? What does it mean that it's binary tree? Binary tree means that every vertex has at most two. But then if it's full binary tree, says that every internal vertex, there are some definitions here, vertex has exactly two or children. These are direct children. So what happens here? So let K be the number of internal vertices. So just rough drawing. So here are all the internal vertices. So the rule says that every internal vertex has exactly 2 descendants. Do you agree? So what? So number of, let's say, children. So K, internal vertices, sorry, have how many children? Each of them has 2 children. Why 2 of them cannot share the same child? Could it happen that we have 2 different vertices and then they share the same child? What would be wrong with that? Yeah, see, you would have a circle. So you start from there and that would finish. So K internal vertices have 2K. Is everybody okay with that? But then what? Then the total number, every vertex is listed here. So if I list all the children, like children are here. So here is left child for 1, right child for 1, left child for 2, right child for 2, left child for K, right child for K. Here are all the children listed. Do you agree? Whenever they, so first, internal vertex has 2 children. Second, and then here's the list of 2K objects. Who's here? Is everybody here?
No, you're missing the root.
Exactly. Everybody's here except the root. So generally, total number of vertices equals number elements of this list, which is 2K plus 1 for the root. Make sense? That's it. That's the proof, nothing else. And then what? So what can we conclude from there? That the total number, so list plus root. That's what reminds you of the reasoning. And then what? We assume that K of them are, let K be the number of internal vertices, and if it's total 2K plus 1, K plus 1 vertices are not internal. What are they then? We call them terminal, which is really external, but the terminal because it just stops, they don't have children. So K plus are not internal, so they are terminal. Here it is. So internal vertices are those that have children, and then terminal are those that don't. So from this calculation, it is a very nice proof and very simple because it's just the same group was counted twice. Once as according to who is producing those children, and the second one is just the general count. And then you compare them to get your result. That's it. There's nothing more. Next question. Yes.
On 13, we have to find the inverse of 16 mod 43. Can you remind me what happens when we get a number that's negative? So like I got negative 8 times 16, which gives you a remainder of 42.
Let me record this so that everybody can follow, particularly our colleagues that are. Oh my. Oh, by the way, I'm recording this, so I will post it on Canvas. I never recorded it before. Someone asked me to record it because they cannot watch it. They have exam now. So we are recording it now, so I hope it shows up correctly so that you are warned about it. So I hope I have your permission. Anyway, So what was the problem? To calculate what was it?
16 mod 43.
What was that?
16
Oh,
mod
inverse of 16 times A congruent to 1 mod 43. Was that the question? Yeah. Okay. So let me just review with everybody that, but I remember on exam 3, almost everybody did perfect job on this. So 43 is what? 2 times 16 plus 11. And you remember I warned you in the lecture notes to distinguish between important numbers and irrelevant numbers, because I noticed a few people that messed it up because they continued with wrong numbers. So then 16 is what? 1 times 11 plus 5. 11 and 5 are important. So 11 equals 2 times 5 plus 1. And that's it. And then what do? We start solving. It is really like actually we are using them as the basis vectors. So generally what? They span the whole space, and including 1. So 1 equals what's from here? It's 11 minus 2 times 5. So these are vectors, 11 and 5, and 2 is scalar. And then what do? We trade the smaller one. So 5 is what? So this is 11 minus 2 times, what is 5? 16 minus 1 times 11. So here they are. And what is important now, why did I put 2 in, right? I have no idea. So that would be what? 11 minus 2 times 16, and then you need to distribute here, not to carry this forever, plus 2 times 11. And then what? You combine the like terms, and you get what? 3 times 11 minus 2 times 16. By the way, what? At this point, can we check our work? Maybe we made calculation error or messed it up. Just calculate 33 minus 32 is 1, which is correct, agree? If it's not correct, I'll go back and correct it. So finally, what's left? 11 is there, 16 is there. I need to trade 11 using 43. So it will be 3 times what? 43 minus 2 times 16 and minus 2 times 16. So this would be 3 times 43 minus 8 times 16. 3 times 2 is 6 of those copies, minus 2 is minus 8. I better make reserved terms here. There are the reserved ones, and again, 129 minus 128 is 1. So that's not what you asked me. You asked me then, what do we do here? Since we are working modulo 43, this is here really congruent 0. So we basically get what? That the negative 8 times 16 is congruent with 1 modulo 43. And this is correct result. The only thing is that we are always looking for numbers that are between 1 and 42, because that's the main congruence class. So generally what you do is just you want a number that's congruent with negative 8, so that the result is the same, but just looks better. So how do we do that? We just add index 43. So generally answer would be negative 8 plus 43, which is 35. Why is 35? First, why do I want that answer? Because it's between 1 and 43, between the main class. Am I sure that 35 would also work? Yes, because we have a theorem that says if two numbers are congruent, modulo 43, the results of operations will also be congruent modulo 43, so not operation of addition and multiplication. So that's what it is. Last step is just add 43.
Oh, okay. So you don't really care if the inverse is negative. I saw on like one question on a quiz a while back, I think you asked specifically for a positive inverse, but
yes. So generally, when I precisely formulate, I should always say positive, and even if I don't say it, I expect positive. So even if
yeah,
it's
so just do that final
positive,
stage. Yeah.
always do this, because not that this is wrong, but this is the most standard way the systems recognize for that. For example, you might have a program that just scans numbers between 1 and 42 and it would reject negatives. So generally, this is the most standard way to express your answer. Although this is really not incorrect. So for example, if I take that 1 point off for not making it positive, you can argue that. And if I didn't put it in the text, I would have a hard time defending I'm trying to send a message, and I always remind myself to put that in the text. But if I forget, just always make it positive.
All right.
Next question.
I just had not a full problem, but a quick question on number 7. When you have two sets and you say A minus B, it's correct to interpret that as the difference.
Yes, so here it is. There are 2 ways people write set difference. So one is this, and that's the most official. So this is called set minus with a backslash. I think that's in Ebb's book. I'm almost sure that she writes it like this. And that's where I carried it for a while, just to not be different. This is, by the way, very bad notation. So even if you see it, don't try to adopt it. Why? Because in algebra, this is used very often, A minus B, but generally A minus B in algebra usually means little a minus b, where you pick a from a, b, you are really subtracting if you have algebra, So then you are really in trouble if in the middle of algebra you have same notation for 2 things. So this is really the official notation. Even if you find it in my writings, disregard it and write it like this.
All right,
I try to be consistent, but as I said, if I somewhere did it wrong, we just cross it. Next question. How did the part about graphs go? Did it make sense? We didn't do too much. So our plan was mostly kind of at the end of the course to have you introduced to the topic so that when you start seeing a little more about graphs in your computer science courses, at least you are familiar with the main reasonings and main terminology. One of the hardest things there is to memorize. I don't know if you remember that section 2, where it was path is this, circuits this, and then simple graph. So there are a million definitions to remember. The worst thing is notation is not always consistent from book to book, from course to course. So then it really gets frustrating. But generally, you saw the main topics about graphs and some main reasonings, and then when you hear a little more, then you have your foundation to build upon. Yes.
Is the final going to be like fairly similar to the practice?
That's always dangerous, because then I would get into problem that I say yes and you say no, but this is not. So that's really complicated to say. What will be similar is number of problems, then distribution through sections. So so like 2 problems on graphs at the end. One will be proof, one will be one construction. Then how many problems from combinatorics and all that. But for example, this one had a lineup for the photo, the other one will completely different. So I would say that level of difficulty is similar. Number of proofs, maybe it was contraposition, now it might be direct proof. So, usually it should be some big topics, not corners, not something that never showed up before.
So like when we did the digital logic circuits, would that be considered like a big topic?
Yes, I would say yes. So that's legitimate. We spent 2 sections, particularly that problem with like binary representation and all that. You remember those? Adding, subtract, yes. No, adding was always, and then yes, and I think we had, yes, there was an 8-bit representation. Yes, that's the one we used. So that could be, or I can ask you, for example, structure over full header, those. So something like that. Or construct a circuit that does this configuration, switches on, to make a table, and from the table to read the configuration or structure. Then, for example, I hope by now you got an idea that definitely I always ask necessary and sufficient condition and contraposition. That's like, one of the main lines in every logic course. So making sure that you can read that correctly and interpret and write. And also very often I ask, is this argument correct or not, or valid? So something like that. Then maybe if predicate formula is correct, is it satisfied when A is 1, B is 2? So that you know how to read predicate formula and interpret its truth value. What else is there? Probably 1 or 2 recursive ones. So as I said, it will give you a practice test, will give you a pretty good idea about the distribution per chapter. But I would say that one can say quite safely that basically it's going to be 7 times 2. 7 chapters, 2 problems per chapter. Roughly, I'm not saying now you count 1, 2, 1, 2, but generally that's the intent, to have them equally distributed. Any other questions or comments? Yes.
For number 15, creating the minimal spanning tree, could you go over how that might look or how it might differ if we follow Kruskal's algorithm and Prim's algorithm? Should those look different at all?
Yes, it might look different, but if they are minimal, then they must have the same total weight. So the addition, when you add all the weights, at the end you should get the same. So that's the only thing. I will either ask you to do one of them, to do both of them, or just say, find the minimal tree however you want. So generally, that's how it will look. So what is the main difference? So it's fairly similar. What is the main difference? In Kruskal tree, you start with all the vertices, and there are no edges. Edges are like on the wall, on the display, and then you just go edge by, you line them up according to the weight, and then say, okay, here is the minimal weight. Put it there wherever it was. So you kind of remove them all. Just keep the vertices, and then pick a minimal one, add it where it was, and then go to the next one, and then just keep adding in the order of increasing weights, keeping in mind that you don't build a circuit. As soon as you build a circuit, just remove that one from the list of the candidates and keep going. That's it. At the end, you will for sure get a minimal span, because it will be spanning. Why? Because it was connected tree from the beginning, so you cannot ruin. Because the only way you skipped an edge was when it would build a circuit. And if you build a circuit, that means you have alternative way to get there, so you will never lose connected. And that's it. What about Prim's algorithm? Then you generally don't start with the vertices. You just add them simultaneously. So you generally add a vertex, then add a vertex with the next vertex that's connected with a minimal edge, and then keep adding. So generally, you kind of have 2 islands: vertices that were added already, and vertices that are to be added. And there must be connection between them, otherwise it would be disconnected. And then you look at the connection between two islands of minimal weight. You add it there and keep going, don't build circuits. So it's fairly simple, both of them. So the second one was Prim's algorithm, the first one was Kraskow.
And on the test, are you expecting us to show steps of connecting something like that, or do you?
You need to give me something. So generally, that was a little problem when you did, which one was that? Yes, when you did that quiz with Euler and Hamiltonian, then sometimes people would not give me enough guidance to see the order, how they did things, So generally, you don't have to do every step of it, but generally you can do 2 or 3 intermediate steps so that at the end we can see it. What's even more important is what happens if you miss one edge for whatever reason. You didn't see it, that there is a shorter edge. You continue with the longer one, and you mess up your minimal tree by a few weight points. And then what do? You gave me the wrong answer. You didn't leave me the trace, so I'll give you 1 out of 12 or whatever it is, which is a pity if you are very close to understanding what's going on. So that's why I would always recommend, not every step, but generally I want to see that appearing. And also you can check your work there better. So just do 2 or 3 intermediate steps. It will be safer for everybody. And it's fairly simple problem, so really it's hard to mess it up. Just be disciplined, line up all the weights on the side so that you know. The biggest problem is there is some edge 7 that you didn't see, and you add 11 before you see that 7. So line up all the weights on the side, and then just keep adding them or crossing them, and then there's nothing that you can mess up. You can program a machine to do it, so there's nothing creative in that process.
You want us to write the total weight at the end?
Yes. Again, if it's correct, then you add up numbers, don't you? I don't think that will assign any penalty. But just it's nice to have like answers. Are there any other questions? So how was the course altogether? Was it okay, or was it too hard, too easy? Did you find something interesting? I usually like to discuss that with my ground classes, but in online class, we didn't get much discussion. We always try in the beginning, and everybody gives up, and then everybody starts doing their stuff. So how would you change the curriculum of the course? What do you think should be a little less emphasized, or what should be added maybe in computer science courses?
I don't know if you did this in the past. I had the old discrete math book you used to use, and it covered finite state automatas, which I think are really cool. Did you used to cover that in your DM courses?
It contained what?
Finite state automatons.
Oh no, we never did that. Yes, it might be even.
It was in the textbook,
Yeah.
the hardback printed one.
Yes, usually, it would be if our course was more pushed toward computer science, and if you would cut off that introduction in logic and all that, that would open the.
Yeah, just not enough room. I understand.
Although very often when you transfer, there will be a course like languages, automata, and all
yeah, and then you get all that.
So generally, I think you will see it quite soon. So, because when you analyze those automata, then you will see something similar to that problem, having 2 ones or avoiding 2 ones or something like that. Generally, you would like, for example, to create automaton producing certain type of sequence or avoiding certain type of sequence. So that flavor was there when we did recursive sequencing. So that will help you a little bit there. No, I do agree. That would really be something appropriate for the course. But I think you were quite busy. That's how.
Yeah.
All right. Did anyone think of any specific questions? What about the organization of the website? Do you have some? Oh yes, you suggested last time that we kind of announce things not only just a week in advance, but maybe 2-3 weeks in advance, so that we can better plan things. I could have done it, but I thought it's better to be reminded. When someone reminds me of something, put my exam, and they do it 3 weeks earlier, that's for sure I'll forget about it. You know? So generally, I thought that kind of timely information is good, but maybe we can do it. Was it easy to access things like files and videos and everything? Did it all work? Okay. There was no problem in the beginning for your 35, second section. Sometimes, yes, I wouldn't make file available. That's a new feature of this kind of software. So I will make it available and I need to be there. And it doesn't tell me that it's not kind of active. And then students tell me, where's our file? But I learned that.
This is the first year with Canvas for you? Yeah.
Yes. So we use Blackboard. So, you know, they're similar systems, but each of them has its own personality. So in Blackboard, when I post something, that's it. I posted it. Obviously, I want it to be visible. No, here it says, post it, and then say, I want them to see it. And that's just different philosophy once you learn. Tian Wang, thought of any questions? Everything's clear? Everything's good? All right. Okay, guys, then if there are no other questions, thank you for coming, and then I hope it goes well. Everybody scheduled it on time, everything's going well. All right, what's my plan with the exam? So people have until Wednesday to take the exams. So my plan is to pick up the exams maybe Wednesday afternoon. So by the end of the day, Thursday, I hope I will be able to grade them all and post your grades on Canvas. Check your Canvas grades if everything looks normal, you know, if something, because, you know, your quizzes, exam grades and everything, so that when I post final, then that's it. What else? Yes, I won't be in town for a few weeks, but then I teach summer session. So if you want to see your final or something, you know, strange, let me know. If some of you are graduating on Friday, then congratulations. I'll see you at the ceremony. That's about it. All right. Thanks for coming. Bye-bye.